Thank you for joining us, folks. My name is Mike Stanley. I'll be moderating this morning's session, tinyML Talks. Today, we're pleased to welcome Jongmin Lee. He's going to be talking about empowering the edge, practical applications of embedded machine learning on MCUs. And Jongmin is a machine learning architecture engineer at NXP Semiconductor. And you'll forgive a pause or two as we switch between slides. We're having some technical difficulties. Oop, there we go. I'd like to thank the tinyML strategic partners for committing to take tinyML to the next level. You can see we have quite a few strategic partners and they make these meetings possible. Also, if this is your first time joining one of these, we want to make sure that you're aware of the fact that we have a tinyML communities on Meetup. You can see the links here for joining us there, as well as the Tiny community or tinyML community on LinkedIn. We also have a YouTube channel with many videos. This video will be joining them after today. We've got 9.5 thousand subscribers and hundreds of videos up there. So lots of good information for you. There is an event coming up in July at the EMEA 2023. If you're interested in attending that event in Amsterdam, please follow the link that you see here. At this point, it's my pleasure to introduce Jongmin Lee. Jongmin is a machine learning architecture engineer at NXP Semiconductor. Throughout his career at NXP, he's focused primarily on developing MCU-based machine learning solutions, and currently his area of concentration is on advancing the architecture of neural processing units. Jongmin earned his PhD degree in electrical engineering from Arizona State University in Tempe in 2017. There, he was a research assistant at the Signal and Information Processing Center, otherwise known as SINCIP at Arizona State University. And I'd like to add a note or two of my own. In 2014, I was working at NXP Semiconductor as a systems engineer, and I had a bright young PhD intern who was recommended to me by Dr. Spanius at Arizona State University. His name was Jongmin Lee. I asked Jongmin at that point in time to investigate the possibility of putting machine learning algorithms on microcontrollers. We didn't even know if it was feasible at that point in time. I asked him just to conduct a feasibility study. 3 days later, he called me into his office and he demonstrated a support vector machine, both learning and doing inferencing on the MCU. This was in 2014. Jongmin was doing machine learning on embedded MCUs long before the term tinyML was coined. So he's been in the business for a while, and with that, I'd like to turn it back over to him. And welcome, Jongmin.
Thank you, Mike San. It was really great introduction. I do remember the first day I did my internship working with you. I think that the first day was very welcoming, and at the moment it was very great experience in my internship there. Thank you for the introduction. And thank you for everyone and also the tinyML community for inviting me to this talk series. I'm Jongmin Lee. I'm working for NXP. It's my great pleasure to have opportunity to share with you very interesting use cases and also project that I have been fortunate to work on with very nice people, including Mike Stanley in the teams during my career at NXP. In this presentation, I will introduce some of MCU-based embedded machine learning use cases, partially from my own work in the past and partially from my colleagues. I do appreciate the contributions from Michael Wang, Jianfeng Qin, and Anthony Hureka by providing me with very nice demo videos and slides to present today. And I also like to thank Adam Fuchs, Ali Ors, Leonard Bernberg for their valuable feedback while preparing this slide deck. Okay. So the contents are in the following. After a brief introduction, I will show some use cases of embedded machine learning on MCU in 3 categories. The first one is anomaly detection. The second is voice control, and finally vision applications. And then I will introduce NXP's neural net accelerator that is enabled in the recently released MCU product. Okay, so let's talk about NXP's machine learning solutions and support before we move on to the main part of the presentation. Some terminologies on these slides are actually also mentioned in the following slide. So I think it's good to address them here. The NXP's EIQ is the ML or machine learning software development environment to enable the use of machine learning algorithms onto NXP's MCU or MPU product. It also provides EIQ toolkit to support various processing to deploy ML models. And the EIQ inference engine also comes with TensorFlow and DeepView-RT. So the whole ecosystem is free to download. So if you are new or if you didn't know about this EIQ software development environment, please try it. It's a very nice tool. And we also develop and offer various types of solutions to customers. The purpose of turnkey solutions, as you can see on the right top of the slide, is to provide near production ready solutions to customers so that they can reduce their go-to-market time for their end products. The turnkey solutions include HMI, vision, voice, and all running on NXP's crossover MCU, which is iDynamics RT series. In this presentation, I will introduce the local voice control solution that I worked in the past. And the Conversa, Voice Seeker, VoiceBot, and VIT are all NXP's own voice technologies. They support custom voice solutions in bigger or broader range of MCU, MPU portfolio. The EIQ Neutron MPU. So actually, I'm currently working in this team, in the team to design the MPU architecture, which is very exciting, personally. The MPU is highly scalable and optimized for low latency and energy efficiency. And of course, we support third-party software and hardware. You can get more information from NXP's website. Okay, let's jump into the main topic. Nowadays, we have seen the move of machine learning and its applications toward edge devices. A lot of people have shown very realistic implementation and product or applications with edge devices. Obviously, there are multiple benefits why we want so-called tinyML at the edge. Deploying ML on embedded devices can reduce data traffic between the edge devices and the cloud. If you think of sensors, for example, such as accelerometer, with sampling rate of, let's say, 100 Hertz, it's very obvious that sending all the raw data to the cloud is unrealistic. It's same for image and voice data as well. Deploying ML model to the edge can also reduce latency and can respond in nearly real time to the input data. Also, it can potentially protect privacy because raw data is not transmitted to the cloud. Machine learning is still mostly performed at the cloud. Large machine learning algorithms or applications are still trained in the cloud servers with large storage and computing capacities. and also even performs inferencing in cloud base. However, as technologies on machine learning algorithms and their related hardware technologies are growing and also improving, we can clearly see that machine learning has been pushed toward edge devices, especially ML inferencing can be conducted in smaller memory footprint and computing power at MPU-based edge devices. When it comes to MCU-based ML machine learning deployment and inferencing, it becomes challenging because the performance is often limited by hardware resources, such as memory, which is typically less than 1 megabyte, and CPU clock speed, that's typically, let's say 300 megahertz, less than 1 gigahertz. However, it's still possible to run lightweight and also optimized ML models with very good performance. So I will show some examples of them in the bottom slide. Okay, so let's talk more about the what are the examples of MCU-based machine learning applications. There are more application domains than just these three, but in this presentation, I'd like to talk within these three categories. The first one is anomaly detection. It's essentially time series data analysis. Typically, we use sensors to get the time series form of the data. Typical use cases would be to classify states or behavior with sensors, or predict potential failures, and so on. The second category is voice with MCU-based platform. Keyword, most realistic use case is keyword spotting to detect wake word, such as as you know, the Alexa or Google, OK Google, or Siri in the well-known product. But not just wake word triggering, but also we can do that can be used for various IoT applications by enabling voice commands as well. Vision applications are probably the most broadly used machine learning applications in the industry. There are various products and applications of image classification, face recognition, object detect, and even personalization based on face recognition as well. Later in this presentation, I will introduce some examples such as multi-person detect and hand gesture recognition, both are running on MCUs. The first application domain is anomaly detection. We can get sensor data in various forms, such as motion with accelerometer, magnetometer, gyroscope, and so on. And an environmental form will be coming with pressure sensors, humidity, or temperature sensors. We also get audio time series data collected by microphone. Combining these sensor data and also advanced MCUs and of course ML models, we can enable various applications. Examples would be machine condition monitoring, that is to monitor mechanical machines, states or behavior or health. Vibration data using accelerometer is one of the most commonly used format of the data. Other applications examples would be environmental awareness or structural monitoring and audio event detection. Okay, so the first thing I would like to introduce is the first work I did in NXP. As Mike mentioned at the beginning, I know it's quite old work, but I would like to talk about very interesting questions we had. Mike, who was as he mentioned, he was my boss at that time. Today he introduced me at the beginning of the talk. He gave me very interesting question. So with Cortex M4 based MCU sensors and sensors, can we implement implement a machine learning, based on anomaly detection. Yeah, we started with raw sensor data logging. Yes, it's obvious. We can collect multiple sensor data simultaneously in real time. And then the next question we had was, can we compute FFT or some statistical features with the general purpose MCU in real time and use them as input features to a machine learning model? Yes, it is possible. The figure on the right top shows a snapshot of SDFT, short time Fourier transform. You can see the trajectory of a peak when a tone sound changes its frequency. By the way, the right axis is the time instances and y-axis is the FFT beam. I think we use the 256 FFT size, and I think the sound was about 8 kilohertz sampling of microphone sound. And then after that, the next question was, can we do inferencing machine learning model for anomaly detection? Yeah, as you can see here, we use the SVM support vector machine model for anomaly detection. At that time, the pink trajectory, the pink triangles represent support vectors. The green dots within the boundary indicates normal states, while the red dots out of the boundary are for abnormal conditions. And there's one more question. Can we actually train the SVM model on the MCU board? Yes, it was possible, although that was limited because of memory size. We use the sequential minimal optimization algorithm to train the SVM model with very limited size of input features. This may not be realistic if the training data size gets bigger, because the complexity of the training SVM is order of n cube. But I think it was very nice, interesting try as for proof of concept. Okay, so the key technical features are in the following. We developed a machine learning that was SVM based on anomaly detection, running in ARM Cortex-M4 based MCU board that has multiple motion sensors. Later, we use the Cortex-M7 based MCU for the anomaly detection application. Same model, same SVM model was used, but with this board, we added more features with various types of sensors, and also added connectivity to Microsoft Azure IoT Hub through Wi-Fi network. We observed that this MCU-based embedded board had enough resources to process sensor data logging, feature extraction, and SVM inferencing. However, the performance was often constrained. We needed more automated way of model optimization and evaluation pipeline. With regard that automated ML optimization, currently my sister team has been developing a very nice tool. It can be generalized to any source of time series data, though. The process in the tool consists of mainly 4 steps: pre-processing, training, optimization, and algorithm generation. All the processes from raw sensor data collection up to the ML model deployment are done automatically with optimized training and validation processes. There is another anomaly detection solution available in NXP's application software pack. The app software pack delivers application-specific production-ready source code. You can actually download the application source code with various examples. One of the examples is the machine learning based machine state monitor. In this specific app software package, deep neural net based anomaly detection model was trained, and it was and this can be also deployed to various MCU-based platforms, and various sensing devices are used, including motions, temperature, and pressure, and audio sounds as well. So related application space would be state monitoring, activity recognition, and machine health. Especially the demo application is to monitor fan state, such as off, on, clock, and friction. Yeah, as I said, you can go to the NXP's website for app software pack, and you can download the source code and try by your own if you are interested, of course. The application, this application was developed using deep learning and EIQ tool. The data type is vibration, and the data was collected for over 10 hours. The ML model is custom convolution neural net based model. It supports multiple platforms, as I said, including the Cortex M7, M4, M33, and the MCXN is the one I'm going to introduce later in this presentation. That is the MCU that comes with neural net hardware accelerator. So application with that MCU is coming. So just keep in mind that, and if you are interested in try the new MCU, which is MCXN. You can go to the website and download the source code. Okay, so the next application is that I would like to present is local voice control. Here, the local means the voice control is purely offline. This solution can be applied for anywhere that needs hands-free private voice control without cloud connectivity. There are two major components within this application, which are audio front end and voice engine. That is actually for keyword spotting. Many customers we had talked with requested echo cancellation and far field features for the audio front end. Echo sound is transmitted from the loudspeaker and mixed with the incoming speech. To remove the echo from the original speech, the reference audio stream and the delay time from the loudspeaker need to be calculated correctly. We had this feature implemented in our MCU-based turnkey solution. And also the other important feature is far field voice enhancement. By using microphone array for beamforming, we used 2 microphones in this solution and 1 additional microphone for optional to further improve the performance. The voice engine was for, as I said, keyword spotting. The engine is always on to detect wake word or wake words. Multiple wake words can be detected. After being triggered by a wake word, the engine detects a command. I mean, the new engine or the command loaded up and start detecting a command. Basically, the engine for wake word and the engine for commands can be separated, although the base engine is common and shared for both wake word and command engines. We can make applications to support kinds of multi-phase wake word and command structure. For example, once the wake word for instance, hey NXP is detected, then the first phase command engine starts running to detect one of the commands such as play or temperature up. And then one of the first phase command is detected, then the second phase command engine can start running, and so on. So it can be also kind of tree structure. So where sequentially you can continue or add up more voice engine and to customize for any voice control solution. So yeah, it's the MCU-based far-field voice control turnkey solution. It's based on ARM Cortex-M7, 1 MB SRAM. For the audio front end, we had PDM to PCM conversion. That is actually to support low-cost PDM microphones. Deep learning based far-field voice enhancement was used. And for the voice engine component, it supports multiple custom wake words and more than 100 commands. And as I explained, we can run multiple wake word or commands engine separately or sequentially. So it is also possible to run multiple wake word engine in different languages. Another interesting feature was to use a PC-based speech model generation tool. You just type text for your command or wake word, and then the tool generates speech model instantly for that text you just typed. I just briefly overviewed about the turnkey solution. There's more details and very detailed guide available on the NXP website with this link. So let me introduce a little bit about the examples of wake word and commands are. What are the example of wake word and commands as shown in the slide? Yeah, as I said, the multiple languages can be supported simultaneously, and the PC-based tool is available. On the right side, just examples of the voice control commands. Okay, so for that voice control solution, I have two demos to show. The first one is to demonstrate far field. This video was taken actually in my house dining area during the pandemic. On the wall, you can see there is a demo kit mounted that actually detects my voice. Let me play it. Hey, NXP.
Can I help you?
LED red.
Okay.
Hey, NXP.
Can I help you?
LED green.
Okay.
Hey, NXP.
Can I help you?
Cycle fast.
Okay.
Hopefully everyone can hear that audio. And the second demo is to demonstrate multilingual feature. There are 4 wakeboard engines in different languages are running simultaneously. It picks up any language's wakeboard and then loads up the detected languages command engine. The following. Starting from English. Hey NXP.
Can I help you?
Temperature up.
Okay.
Since I'm not a multilingual, let me use the Google Translate. For Chinese.
你好，恩智浦。我可以帮你吗？温度升高。好的。
Okay, for German.
Hallo NXP. Kann ich Ihnen helfen? Temperatur erhöhen. Okay.
For French.
Salut NXP. Puis-je vous aider? Augmenter température. OK.
Okay, next. Okay, so let me describe some numbers on the performance. The exact numbers can be different depending on how custom solutions are developed. For the RAM utilization, it takes approximately less than 500 kilobytes or 80 kilobytes for one language. But this number 480 kilobytes includes everything, including like audio front end with 2 microphones and other remaining runtime components as well. It adds up, by the way, approximately 50 kilobytes for each additional language, with the exception with the Chinese languages, because that Chinese language takes with the specific characteristic such as 4 different tones in their language. So it takes approximately about 90 kilobytes, and the CPU utilization also varies with how many languages are implemented in runtime. It is also possible. It's very approximate number shown in this slide. It is also possible to customize for optimal utilization. We can remove, for example, echo cancellation to save some resources if that is not needed, just as an example. And we can down the utilization, the CPU utilization, to the approximately like 25% of the Cortex M7 CPU. So next application is multi-person detection. The ShuffleNet V2 was trained with Coco and Pascal VOC dataset. The model is then converted to an executable by EIQ toolkit. We developed a FreeRTOS-based system that is called MicroVita, microcontroller-based vision intelligence algorithm. That is a system to efficiently manage camera, display, or algorithm task in FreeRTOS. This person detector model is also executed both in the iDynamics RT1170 and RT1060 EVKs using EIQ tool. Both EVKs are with Cortex M7 MCU, but the 1170 EVK supports up to 1 gigahertz. So you can see the different latencies on these two boards for the person detection. Again, the source code will be released in application software pack. The application software pack I mentioned previously in the slide, in previous slide. There are many examples, including anomaly detection and this vision person detector. I'm not sure it is right now, is it released or not, but I think it will be released in application software packs. Okay, the demo for that person detector.
The following clips show the results of the project. This first clip shows that the people can be accurately detected on the IMX RT1170. This can be used in applications to count and track people. Here, it shows the robust performance even when the human body is facing away from the camera. A more challenging case is when people are sitting, as the furniture will cover parts of the human body. In this application, the person detector still provides the expected bounding boxes of the real people. More importantly, it does so in near real time.
Okay, I have another vision application, which is the gesture recognition. Using the Google Hand Landmark model, it first detects a hand and then detects whether it's the left hand or right hand, and finally make a decision for a gesture. It is quantized and also customized CNN-based model. It will be released in the smart HMI RT1170H turnkey solution as a kind of demo level solution. By the way, the HMI RT1170H is the turnkey solution, but this specific gesture recognition can be included as a demo level solution. Okay, so yeah, you can see the guy on the screen is Michael Wang, my colleague, former colleague. He is showing different hand gestures. First, the model detects the hand segment, and then recognize a different gesture. Okay, now let's talk more about our latest MCU that comes with neural net accelerator. So for the past several years, we have seen great performance improvement in terms of latency and energy consumption by, for example, model compression techniques. For example, quantization provides lower energy consumption as well as lower latency. On the left graph, the 8-bit quantized model can achieve lower latency than a flow model at the same level of accuracy. And also, we can see on the right table, the lower bit operations can consume lower power, which is quite obvious. So on top of that, enabling hardware neural net accelerator can also provide significant improvements. For example, by leveraging the reusability of 2D or in general convolution operation in convolutional neural net model. So mathematically, convolution can be treated as matrix multiplication. Let's consider we have 2x2 weight kernel and 3x3 input. The first output is the sum of multiplication in the green box, and the second output is the sum of the multiplication in the orange box, and so on. So it's basically repeat of multiply and accumulate. We can represent this as a matrix multiplication in 1x4 row vector and the 4x4 scale matrix. But you can also observe that there are multiple values are duplicated. For example, on the second row and the first column, 2 is actually also reused on the first row and the second column. And there are more values are reused in different row or column location. We can draw this operation like this. If there is only one single MAC to process matrix multiplication, for this specific input and weight pairs, the MAC should be iterated 16 times at worst scenario. However, as you can see on the right side on the slide, the weight values are reused for the first segment of the input data. And if we use the multiple MACs in parallel, the input data can be also reused intuitively. Intuitively, if we think of the nature of convolution operator. So once we fetch the input data from the memory, if we broadcast and reuse them in the following operations, then we can save more time. In this specific example, the value 2 and 5 in the second input, in the second input segment are reused from the first input column. and so on. So we have 4 and 5 as actually reused from the first input segments. So this specific drawing only shows the single output channel, and I mean, what I'm saying here is that we can reuse the data as well as the weight, and we can also leverage the parallel architecture to accelerate the convolution operator. That is actually matrix multiplication. So I am only showing here is a single output channel, but if we think of the multiple output channels, I think the benefit to use this reusable data and parallelism can be increased.
Jongmin, this is Mike, just jumping in to give you a time check. It's about 18 minutes to the hour right now.
Okay, thank you. So let me speed up a little bit. Recently, NXP has released a new MCU that is called MCX. And the N series has the neural net accelerator and other very nice blocks, as well as such as DSP accelerator as well. Yeah, NXP won the best ML processing MCU award in the last tinyML summit this year. Okay, the neural processing unit is optimized for performance and energy efficiency for neural net inferencing. It is designed to accelerate matrix computation to reduce inference time. And it comes with EIQ ML software development environment. On the left side of the slide, it shows the block diagram. It has multiple compute pipeline, where each pipeline compute 4 max per cycle. Data canvas is very important to support data reusability and before feeding the data into the pipeline. Dequantization, scalar, and activation are executed in each pipeline. So we have 4 rescalers and activations in this specific block diagram. And with that, for this MCX N-series MCU, we can achieve 6 giga operations per second. As you can see, how the numbers are calculated at the bottom of the slide. Okay, so with this EIQ neutron NPU, we can achieve over 30x relative acceleration compared to the use only single core alone. And I mean, the single core is the Cortex M33. And we can also achieve 37x less energy consumption. Some example operators are shown in this graph, such as 2D convolution, pointwise, and depthwise convolution that achieves very great acceleration. There are more operations, of course, supported. Yeah, you can check EIQ neutron software development for more details. And okay, now it's the demo time again.
Hi, I'm Anthony Hirica, and I'm demonstrating facial detection using the neural processing unit that can be found on the new MCX microcontroller family. This is using the MCX breakout board and has a camera connected using EZH Smart DMA and a LCD screen connected using FlexIO. We've seen some significant performance improvements using the neural processing unit, up to 50 times faster inferencing times on MobileNet, for example. And so we're really excited about this new technology.
Okay. I think that's about it. So let me, if I summarize my presentation. So deploying lightweight machine learning models on MCU-based edge devices have shown very good performance, as I shown in some examples of the in different application domains, including anomaly detection, voice control, and visions. on top of that, with recent advancement such as enabling neural processing unit to MCU hardware, that can significantly accelerate ML performance at the edge devices. So I think we have more potential possible improvement in the future. Okay, so yeah, so there are some NXP EIQ related resources you can check. If you are interested in, please take more time to review these slides with these links. And there are also kind of general machine learning AI training series on the NXP website that comes with some hands-on experience with NXP's MCU and MPU product and solutions. And of course, for more information on our NXP's products, please visit the website. Or if you want to get some hardware or the kit and to know more about the purchase the product, you can also visit our distribution partners. Okay, I think that's all. Yeah.
Thank you, Jongmin. So we've got a few minutes left for questions. So let me try to summarize a few as we go through. First one is from Jose Ramos. Jose is interested in using products like Alexa, for instance, to assist older folks. So he says older folks also need to assess voice assistants like Alexa, but forget or can say the wake word. Can tinyML help? And then he followed up with, could I clap my hands and trigger a wake word command? This would help elders with ADRD.
Yeah, I think we do have Alexa actually voice turnkey solution. I just realized I didn't include that turnkey solution. We do have the evaluation kit, especially for Alexa implemented. So yeah, that can be also used for elder people, and of course for wake word and also the voice control as well. I mean, combined with the local voice solution.
Great. So the next question is from Mohammed. He's asking, are ESP32 modules suitable for anomaly detection?
I'm not sure about the ESP32.
Yeah, I was going to add to that. I don't think either you or I have used those. I suspect that they could be used for anomaly detection, but given that Jongmin is with NXP, he hasn't had a chance to be working on that particular platform.
Mm-hmm. Mm-hmm.
Okay, the next question is from another anonymous attendee asking what ML/DL framework is integrated into MCU to run the models. I'm thinking about TensorFlow Lite Micro, Onyx, or custom framework. From the user perspective, what kind of format should we convert our trained models to in order to be able to run them?
So as far as I know, we have EIQ tool to convert, including TensorFlow Lite or TensorFlow Lite Micro and Onyx, and some other commonly used model type format. I think if you check out the EIQ software development environment, probably you can get more ideas how the model, what kind of format can be also converted. So I think please go to the EIQ website to get more information.
Yeah, I'm no longer with NXP myself, but I know back in my days with the company, we were definitely involved in all of those areas.
Yes.
Next question is from Sean asking, is it possible to add additional languages apart from the 4 which are offered by the turnkey solution? For example, Polish or Spanish?
Yeah, I think actually I didn't include what languages are available for that local voice control turnkey solution because the work I did was about more than a year ago. So they updated more languages. Yeah, I have the list of the languages that is supported, but you can also check out the link, the website for that local voice control turnkey solution. There is a list of languages available, and for the latest support, I think the Polish shelter, I think is also supported. I mean, at that time, about a year ago, it was more than 40 languages supported, and they are adding more. I mean, the team is adding more languages as well. So most likely they support those languages that you asked. But please make sure check out the website, or there's a contact email if you check out the website. I think the local comments at nxp.com, but just double check in the website and send that email to them, to that email, and probably you will get more detailed information about the language support.
Okay. The next couple questions, I believe, are relating to the hardware acceleration that you were talking about. The first question has to do is that binary values can be derived in this channel? I'm not sure which channel they were referring to. And then the second question was, can the MCU be used for concurrent conventional MCU time-critical tasks and perform offline non-time critical ML inferencing?
The first part, actually, I'm not sure if I understood correctly. Yeah, binary and which channel? Sorry,
Okay,
I don't know.
We may need some more clarification on that particular question, Sal, if you get a chance to submit it. And just repeating the second question, can MCU be used for concurrent conventional MCU time-critical tasks and perform offline non-time critical MCU ML inferencing?
I'm not sure. Yeah, to make a clean answer, but so basically,
let me take a stab at it if I can help out here. The answer is yes, Charles. You can do that. You'll note that Jongmin presented CPU utilization rates earlier in his presentation. It's always a juggling act in terms of how much you can do within the constraints of a given MCU. So it's going to be application specific, but yes, you can do both ML and other activities concurrently. And then the last question before, actually a couple more here questions. How close are we to host GPT on tinyML platforms?
Yeah, so GPT. So yeah, to be honest, I don't know. But very recently, we have seen a very interesting work using transformer to run sort of like GPT, like chatbot using TensorFlow Lite. But yeah, it was a nice demo. I don't remember exactly, but probably it's very
it's going to be a while.
It's going to be a while. But I do see some work that using TensorFlow Lite for transformer type of application.
Interesting.
Yeah.
The next question is from David Ramirez. Is it possible to utilize the active learning training strategy on board the device for these voice and vision modules?
Active learning means
learning on the fly, I believe.
Yeah, learning on the fly. Yeah, I think that was my guess. Yeah. So I think, although I'm not, went to the deep dive on that direction, but yeah, I think it would be possible. Yeah. Great. There are a lot of work on device learning, and that should be also possible for MCU level.
Super. Well, that runs through the end of our questions, Jongmin. I want to thank you for putting together a fantastic presentation. It's always interesting to me to see the continuing progress in this world. So thank you for pulling it together and being a part of it. Thank again our tinyML strategic partners for committing to take tinyML to the next level together. Our executive strategic partners, Edge Impulse, the leading development platform for Edge ML. Qualcomm AI Research, advancing AI research to make efficient AI ubiquitous. Accelerate your edge compute with Sentient, making edge AI a reality. Our platinum strategic partners. Renesas is enabling the next generation of AI-powered solutions that will revolutionize every industry sector. Atrios, deploy vision AI at the edge at scale. Our gold strategic partners, Analog Devices, where what if becomes what is. Arduino Pro, easily deploy your tinyML solutions with Arduino Pro. ARM AI, and here you see the links for ARM AI virtual tech talks. And Infineon, driving decarbonization and digitization. They're testing my ability to enunciate correctly today. Inatura, neuromorphic intelligence for the sensor edge. Microsoft. And SenseML, analytics toolkit suite. The right AI can make or break your next smart IoT product. And ST Microelectronics, providing extensive solutions to make tinyML learning easy. Synaptics, engineering exceptional experiences. And here are our silver strategic partners. I want to thank them as well. And please note, all the material is copyright 2023 by tinyML Foundation, all rights reserved. And with that, we want to thank you all for your participation today. And please join us for future tinyML events.